In the last video, we talked about the machinery of stochastic calculus, the Itô calculus. It has one additional term relates to the second order of the Taylor expansion. Basically, the change of Brownian motion square survives, and that equals to the change of time, dt. This is related to the quadratic variation of the Brownian motion. The main topic today is the stochastic differential equations, SDE. In the most general form, it can be written in this way, where the change of the process dxt equals to a drift that's depending on time and the process itself, plus a fluctuation term where the standard deviation depends on both time and the process. So the solution to that, the xt, is also known as the Itô process. One famous example for that is just the stochastic process for the stock price given by the geometric Brownian motion. Basically, if you think about xt as the stock price, so both the drift and the fluctuation is proportional to the stock price xt. So you can think of it as a percentage drift and percentage fluctuation. For example, if mu equals to 1% and sigma equals to 3%, then basically the percentage change of the stock price, delta xt over xt, that follows a normal distribution with mean of 1% and a variance of 3% square. And I should say this is per unit time. So this is the idea behind the geometric Brownian motion and why we want to use that to model the stock price. So our main goal today is to solve the stochastic differential equation using Itô calculus. This problem is difficult in general. The main reason is that for Itô calculus, not only the process depending on two variables, time and the Brownian motion, but also we have the second derivative in Itô calculus. So that is exactly why SDE is difficult to solve. So let's actually look at the example of the geometric Brownian motion to see how we can solve this equation. The idea is that if we're doing regular calculus, we can just perform a separation of variable. So we can just move xt to one side. So that's equals to mu times dt plus sigma times dbt. Now, because we have a stochastic process for xt, so it's good to be very cautious here because we don't just want to naively integrate over both sides. Because in the case of stochastic calculus, the integral of f prime xt dxt does not equal to the integral of df xt. So it does not equal to f of xt. The reason is exactly because Itô calculus has a second order derivative we need to consider. So a good strategy here is just to apply the change of variable directly. So we can define yt as the log of xt. So basically how we come up with change of variable is usually just take a sensible guess. And if we look at this equation here, if it's ordinary calculus, then that looks like the log, right? So we just directly define that. And now we can just apply Itô calculus to get the differential of that. Basically, our function f is log x, right? And let me just write its derivatives first. So we don't have any derivative with respect to time. And the first derivative with respect to x is 1 over x. The second derivative is 1 over x squared, negative 1 over x squared. then we can just apply Itô calculus, right? So okay, we can expand this differential into the second order. And for the square of the differential, right? And if we expand it, right, we'll have mu square xt square times dt square plus 2 times mu sigma xt square dt times dbt plus sigma square xt square dbt square. So the first two terms is not going to survive. And for the third term, we can replace the dbt square with dt. So now we can just plug in everything into this equation. So we'll have 1 over xt. I'm just going to swap out the dxt as mu times xt dt plus sigma times xt times dbt plus a half. Second derivative is minus 1 over xt squared times sigma square xt squared dt. So there are many things can be cancelled. And we will have mu minus a half times sigma square dt plus sigma times dbt. So that equals to the differential for the log of the stock price. Okay, so the idea is that after this change of variable, it's safe to integrate both sides. Now, if we look at the terms related to the Brownian motion, this is not depending on the stochastic process anymore. We just have a constant times the Brownian motion. So that's why we can integrate it directly. So the reason is because the integral of sigma times b dt is just going to be the Brownian motion scaled by sigma. That is okay as long as the sigma is not a stochastic process. It is not depending on the Brownian motion. You just have a constant sigma. And let's set the bound of this integral from 0 to capital T. Right, it's just going to give us the log of xt minus log of x0 equals to mu minus a half sigma square times t plus sigma times the Brownian motion. This is exactly how the log-normal distribution is defined. So alternatively, you can say that xt is log-normal, follows log-normal distribution. Right? I'm not going to write down the parameters, right? But it simply means that when we take the log, it follows normal distribution. So if we go back to this entire derivation here, right? So since the special thing is that after the change of variable, the change of the Brownian motion, the dbt term, is only scaled by a constant sigma. So that is exactly why this change of variable works. So it just means that if you have like a general stochastic differential equation like this sigma depends on the stochastic process, right? That is not good. We need to find the magical change of variable to make it constant. What about the general stochastic differential equation? How can we solve this equation when there isn't a simple way of changing variable? So a very powerful approach in practice is just a numerical simulation. So let's say that we want to sample a path from 0 to t. And then we can just sample the change of the process, and that will give us a stochastic path. So let me just denote these intervals as T1, T2, T3, all the way to Tn. And then if we look at the difference, the xti plus 1 minus xti, so that equals to delta xti. And using the equation, it is approximately mu of ti xti delta t plus sigma ti xti and b delta ti. So we just basically use the initial value to plug in the function mu and sigma. Basically, in a small time interval, this quantity stays the same. They stay constant within ti, within delta t. So this is approximately. And if we look at this formula here, that is basically a Gaussian distribution with mean and variance. So during the simulation, sometimes we can just sample from a standard normal distribution and then transform it linearly. So the idea is that we can just sample z from a standard normal. Then the difference will just be mu delta t plus sigma delta t times z. And using this procedure, we can get a path. Because let's say that our starting position is x0, then we can obtain x1, x2, all the way to xn. But just gradually sample it from this distribution. And then each time, all we need to do is just to plug in the stochastic values into the formula mu and sigma. Well, this is a very simple idea. And using this procedure, we can sample many paths from the stochastic distribution. That has many applications. The stochastic simulation is a very powerful approach to handle stochastic processes. It allows us to directly sample paths from the differential equation. So when we sample n different paths, that will form a probability distribution. For example, if we look at one particular time snapshot at time t, then we'll have an empirical distribution given by a histogram. Using this histogram, we can find the density function from it. And another application for the stochastic simulation is the Monte Carlo approach. The idea is that if we want to take the expectation of something, you can just directly take the average using the simulation. This is related to the option pricing. So the option is simply a function defined over the stock price. With the Monte Carlo approach, we just approximate this expectation with the average. So we basically just plug in the simulated value. Okay, let me just call this xt to make it state consistent. The idea of Monte Carlo is very simple. We just use the sample average to replace the expectation. Okay, so that is pretty much about this video. We looked at how to solve the stochastic differential equation. In some special case, we can solve it directly, such as the geometric Brownian motion, which gave us the distribution of the stochastic path. Or we can just use stochastic simulation to sample the path given the differential equations. And when we sample n different paths, we can look at the population behavior, such as the density function or the expectation. So this simulation approach is actually an alternative to the PDE approach. So basically, if we want to estimate the probability density, we can use the Fokker-Planck as an alternative approach. So that is the topic for the next video. The Fokker-Planck equation can tell us the evolution of the density function, which means solving the Fokker-Planck equation can give us the probability density function. Then for the Monte Carlo approach, there's another PDE associated with that, known as the Kolmogorov backward equation. So basically, the Black-Scholes equation for the option pricing is a special case of that. So basically, the Kolmogorov backward equation can tell us the evolution of the expected value. And we'll derive this equation after the Fokker-Planck video probably.